Welcome to part 2 of our ARSET training on estimating surface PM2.5 using satellite data and other information sources. In this part, we'll be learning about the estimation of PM2.5 from AOD and discussing the methodologies and available datasets using these methodologies to create PM2.5 estimates. The trainers for this part will be Dr. Aaron von Donkelaar, a research associate at the Washington University in St. Louis, Dr. Pawan Gupta, a research scientist in Goddard Space Flight Center, and they'll be joined by Dr. Junhyun Seo, an assistant research scientist at Morgan State University. Our objectives for this training will be, by the end of part 2, that participants will be able to explain the geophysical, hybrid, and machine learning methodologies used to infer surface PM2.5 from satellite AOD information and other data sources. Second, we hope you'll be able to differentiate between these available data products for surface PM2.5 from NASA and Washington University in St. Louis based on their methodologies and the strengths and weaknesses of the two data products. And finally, you'll be able to use NASA tools and the SatPM website to access these surface PM2.5 data products for a region of interest and a time period of interest to you. Recall from part 1 last week that PM2.5 is a measure of the in situ mass concentrations of particles smaller than 2.5 microns in aerodynamic diameter, and that aerosol optical depth, or AOD, is an optical measurement of the atmospheric column aerosol loading, that is, the total presence of aerosols in the atmosphere from the surface up to the top of the atmosphere. AOD can be well related to PM2.5 under certain conditions, but that relationship will degrade or break down if, for example, the aerosols are prevalent in the atmosphere well above the surface level, if coarser particles, that is particles larger than 2.5 microns, are dominant among the aerosols, if the aerosols are absorbing water, and if the humidity is variable and the particles absorb water under high humidity conditions, if the atmospheric or the surface conditions prevent reliable retrieval of AOD, for example, over highly reflective surfaces or under dense cloud cover, if the spatial resolution of the AOD does not capture the local PM2.5 variability as measured by ground-based PM2.5 monitors, or if the timing of the PM2.5 measurements does not well coincide with the satellite overpasses. As a reminder, if you have any questions during this part, please put them into the questions box and we'll address them all at the end of the webinar. You can put the questions in as you go. We'll collect those questions, and those questions, along with the answers, will all be posted in a document, which will be available on the training website about a week following today's training. So with that, I'll hand things over to Dr. Aaron von Donkelaar to talk about geophysical and hybrid PM2.5 estimation methods.
Thanks, Carl. So last week we touched on using a simple linear regression between ground-based observations of PM2.5 and satellite retrievals of aerosol optical depth as a means to use AOD to locally estimate PM2.5 concentrations. We saw that in certain cases this simple approach works really quite well, but in others there can be some severe limitations. For this part of the workshop, I'm going to focus on two other methods of using AOD to estimate PM2.5 that specifically seek to either avoid the use of ground-based observations altogether, or at least ensure the information they provide can be applied over a larger area. I wanted to start by showing the density of publicly available ground-based PM2.5 observations around the world. Here I've updated a figure from Martin et al. 2019 to show the average population-weighted distance to ground-based monitors for countries around the world. You'll note that this average proximity can vary quite significantly, with populations in large regions of North America, Europe, and China, as well as a few others, typically residing within less than 50 kilometers of the nearest PM2.5 monitor. Populations within South Asia as a whole typically reside within 70 kilometers, Central Latin America within 130 kilometers, and North Africa, Middle East typically within a few hundred kilometers. Even over a monitor-dense region such as North America, the typical distance can vary significantly, from less than 15 kilometers over western states to 25 to 50 over more central ones. The net impact of all this, with respect to estimates of PM2.5 from satellite, is that any method that seeks to be globally applicable will need to either minimize its direct use of ground-based observations or find an effective way to account for how the relationship used between AOD and PM2.5 changes with distance from the monitor locations used to constrain that relationship. One way to deal with this challenge is to remove the need for PM2.5 monitors altogether. To do this, we need to revisit a relationship that was introduced to you last week that calculates AOD given PM2.5 concentration or set of assumptions, namely that skies are cloud-free, the aerosols are well mixed with none above the boundary layer, and lastly that the aerosols present are optically homogeneous, that is, similar. Given these conditions, you can see that AOD is proportional to PM2.5 concentration itself, as well as the boundary layer height and the extinction coefficient, which relates to how much the aerosol in question attenuates, that is, scatters or absorbs, any passing light. Particle effective radius and density are inversely related, with the potential for an additional effect from relative humidity if the aerosol is hydrophilic. In order to broaden the applicability of this equation, we can relax a few of the initial assumptions and rearrange to solve for PM2.5 given the retrieval of AOD. Here, rather than assuming the aerosols are well mixed throughout the boundary layer, we're going to assume that we know the fraction of AOD that occurs near the surface, up to a height of delta Z, and is associated with PM2.5. We also remove the assumption that there is no aerosol above the boundary layer and that all the aerosol are similar, instead just focusing on the qualities of those near-surface aerosol. With the exception of this fractional term, the formula itself is quite similar, except that now the variables related to aerosol properties are no longer representative of the entire boundary layer, but again, just of those aerosols that are near the surface within that delta Z height. This equation, shown again here, forms the basis of the geophysical method to estimate PM2.5 from AOD. It is theory-based, physically driven, and completely independent of ground-based PM2.5 observations. The challenge, however, is that it requires some assumptions or knowledge about the aerosols that are producing the retrieved AOD. This includes information about aerosol type, which impacts the density, effective radius, and extinction coefficient. It also needs an understanding as to how those aerosols respond to changes in relative humidity. And lastly, it requires some knowledge about the vertical profile, that is, how much of the local aerosol are located near the surface, or again, within that delta Z height. For simplicity, this large mass of terms relating AOD to PM2.5 is typically reduced to a single scalar term called eta. The challenge of the geophysical method is how to best represent eta. This is where chemical transport models play an essential role in most applications of the geophysical method. As a reminder, a CTM is a computer model that simulates atmospheric composition using the physical and chemical equations that govern the state of the atmosphere. It does this by inputting assimilated meteorology and natural and anthropogenic emissions into the model and allowing those equations to represent the atmosphere's chemical and dynamic response, as well as the transport and deposition of these individual chemical constituents, or tracers. A CTM provides a complete representation of the atmosphere and, in the context of geophysical PM2.5, provides all the information we need to calculate eta. Here we have an example of a CTM predicted eta, in this case for the month of July 2023. The different colors are associated with the contributions of different aerosol types to eta, with yellow for mineral dust, blue for sea salt, green for organic aerosol, black for carbonaceous aerosol, and red for inorganics, being sulfate, ammonium, and nitrate. The eta values plotted here represent the relationship to instantaneous rather than 24-hour PM2.5, and you can very clearly see a pulsing in intensity that circles the globe with a diurnal rhythm. This corresponds to the impact of solar heating on boundary layer height, essentially diluting concentrations at the surface as the boundary layer increases with rising temperatures associated with daylight hours, which in turn alters the vertical structure to decrease the value of eta. Also visible are the regional differences in the particular aerosol sources and types driving the AOD to PM2.5 relationship, such as dust emissions over the Sahara, organic carbon via biomass burning over parts of South America and Central Africa, or anthropogenic inorganic aerosol over China, Europe, and North America. You can even see the impact of the long-range transport of dust and biomass burning plumes, where eta essentially drops to zero, implying that the aerosol is almost exclusively aloft, and therefore the relationship between AOD and PM2.5 is effectively removed. As is pretty clear from this example, using a CTM to represent eta has some definite advantages. You can see how the spatial and vertical variability impacting eta is captured via the model's response to emissions and meteorology. Temporal variability is also captured, which can have advantages when compensating for satellite overpass times and sampling. And also quite clear is the global applicability of this approach when compared to limiting yourself to just those locations that have dense ground-based observations. Counter to these advantages, of course, a CTM inherently has limitations to its resolution, whether by code structure or resource limitations, and most global models are typically run at a resolution on the order of 100 kilometers or so. Any model is also, of course, only as good as the inputs that go into it, and regional uncertainties in emission inventories or meteorology will impact the quality of the simulation. It should also be noted that while these simulations can be quite effective at representing general features, individual events are much more of a challenge and often limit the most effective applications of a simulated eta to longer-term means. And lastly, even at 100-kilometer resolution, these simulations are quite computationally intensive to run, which can limit an individual's ability to run these simulations themselves and require a dependency on whatever simulation output is already available via other sources. All that said, a CTM-based simulation of eta is often an effective means to quantify how AOD relates to PM2.5, especially as the distance to the nearest ground-based monitor increases. Here you can see an example over Eastern Asia, primarily China, for annual mean values during 2021. The left-hand column shows AOD, whereas the right-hand column shows the corresponding geophysical PM2.5. Black dots show the locations of the ground-based monitors used for the comparisons in the lower row. In this example, you can see quite clearly that AOD is well related directly to PM2.5 concentrations over this region, with an R² of around 0.4. Converting this AOD to PM2.5 using a simulated eta not only allows a direct interpretation of this AOD as PM2.5, but additionally improves the R² to approximately 0.5. This example nicely shows some of the strengths as well as some of the challenges of this geophysical approach. You can see how major spatial features in PM2.5 are captured and even improved upon compared to AOD alone, and unlike AOD, the air quality implications can be more directly interpreted. On the side of challenges, there is potential for bias and scatter, which is difficult to evaluate without some level of ground-based observations. As a result, purely geophysical estimates are typically best used for large spatial and temporal scales. Of course, ground-based observations do not strictly have to be used for only evaluation and can also be used to understand any biases present in the geophysical values. This idea forms the basis of what is known as hybrid PM2.5 or geophysical hybrid PM2.5. Hybrid PM2.5 essentially builds on geophysical PM2.5 using ground-based observations. To give an example, here I've shown the difference between ground-based observations of PM2.5 and coincidentally sampled geophysical estimates. As you look at this figure, you'll begin to notice regional structures and features within these differences, such as a large-scale underestimate of a few micrograms per cubic meter on the part of the geophysical values in the southeastern US, and a large-scale overestimate of the same magnitude over the northeastern Great Lakes region. We don't see these large-scale features over western regions, but rather we see a high degree of variability between seemingly neighboring monitor locations. Hybrid methods, therefore, look at these features using statistical models and training to predict biases in geophysical PM2.5. In other words, these hybrid methods predict limitations associated with AOD retrievals and eta simulations and their geophysical implications. So how do we do that? Well, multiple statistical techniques can be used to make these associations, but perhaps the most intuitive approach uses multiple linear regression. From last week's session and from other work, most of you will be quite familiar with single linear regression, such as the example shown in the upper right. Here, a line of best fit is created between a single independent variable, x1, and some other desired dependent variable, y, with a slope of beta 1. One way to think of this result is that beta 1 shows the response of y to changes in x1. Multiple linear regression is an extension of single linear regression where, as the name implies, multiple dependent variables are used. Rather than fitting a line of best fit, you're fitting a plane, but the concept is very similar, and the result produces a series of predictor coefficients, denoted by betas in this case, that can be interpreted as the linear response of your dependent variable to each independent predictor variable. For some systems, these beta predictor coefficients are a universal truth. That is, they don't change in space or time. But for our particular application, estimating the bias in geophysical PM2.5, this is unlikely to be the case. As a result, an extension of multiple linear regression called geographically weighted regression, or GWR, is recommended. In effect, GWR allows the predictor coefficients from MLR to vary in space. In the equation shown here, this is denoted by the addition of the I and j subscripts, which are simply identifying different locations on a grid, such as the one shown on the right here. In practice, the spatially unique coefficients are calculated by running a series of MLR regressions, one for each location on the grid, where the data points used for each regression are modified based on their local significance. This can either be through some sort of weighting scheme associated with the data points during regression, or their removal entirely if they are not relevant to the location at hand. It's worth noting also that, while grids can be regularly spaced, such as I've shown here, they can also be irregular in nature. An irregular grid can be advantageous to capture changes in these relationships in regions where we either expect rapid relational changes in beta or have additional training capacity due to more ground-based monitors, or alternatively reducing the computational costs associated with running on a fine grid over regions where neither of these conditions are expected. Okay, so what variables are going to be most effective at predicting the geophysical bias? Well, the answer would really tie back into one of two sources, either uncertainties in the retrieval of AOD itself, or uncertainties in the relationship that's being used to relate AOD to PM2.5. Between this week and last, we've covered a lot of the sources of this potential uncertainty, which typically falls into four broad categories. Firstly, composition. Different aerosol types can be associated with different optical properties that may challenge AOD retrievals, but probably more impactful in this context is the associations they can have with different emission sources, vertical profiles, and growth factors, all of which impact the AOD to PM2.5 relationship. In this way, the presence of a particular aerosol component, such as mineral dust for example, could be insightful due to uncertainties in the simulated representation of its emissions or transport, which in turn have the potential to bias ADA. Similarly, meteorological inputs also feed back on ADA within a chemical transport model, with local winds and temperature impacting several natural emission sources, for example, or atmospheric conditions impacting the chemical production of aerosol. Land type information can also be related to emission type uncertainties, but primarily I tend to think of this sort of predictor as being associated with uncertainties in the AOD retrieval itself. The dominant assumptions in satellite AOD retrievals typically relate to the amount of light that is reflected off the Earth's surface, which naturally is strongly connected to the type of surface that is doing the reflecting. Urban and desert biases, for example, have both been documented and improved upon in AOD retrievals over the years, but surface type remains a solid predictor of some of the challenges facing an AOD retrieval, and any bias in AOD will directly carry forward into a bias in geophysical PM2.5. Lastly, elevation, or more specifically, changes in elevation, can be an important predictor in geophysical bias. In this case, what is being represented is not so much of an error on the part of a model to simulate ADA, but rather changes in the AOD to PM2.5 relationship that are occurring at a resolution below that of our simulation. You'll recall that simulations are often run at 50 or 100 kilometers. A mountain or valley can often occur at scales well below this, with obvious implications for how AOD relates to PM2.5. In essence, a predictor such as elevation changes is not so much accounting for errors in a model, which could be correctly representing the average conditions at the simulated resolution, but still need adjustment to account for the impact of features that occur below the model's resolution. Bringing this all together, we end up with a GWR-based equation such as you see here, where the difference between the ground-based observations of PM2.5 and their coincidentally sampled geophysical estimates are locally regressed against a series of predictor variables associated with simulated composition, meteorological parameters, elevation parameters, and land type parameters. And below you can see an example of the results that can be obtained. On the left, we have the original biases that were observed against the ground-based observations, and on the right, we see the total GWR predicted bias in the geophysical PM2.5. You can see how this approach captures the major features we discussed earlier, such as the overestimate in the Great Lakes region, but beyond that, it predicts that this feature extends further north and west into parts of the Canadian prairies, a region with far less ground-based constraints. One of the real strengths of this GWR technique for predicting biases compared to some recent and arguably more advanced machine learning techniques is the relative ease of understanding the impact of individual variables and how they shape the overall bias prediction. For an example, I've plotted here both the predictor coefficients and net impact of the nitrate and percent urban variables on the overall predicted bias. As you can see, in this case, nitrate largely explains and gives shape to that Great Lakes region overestimate, as well as its extension to under-monitored regions. This opens up a question about what it is about nitrate that produces this bias. In this case, potentially related to uncertainties in either the chemical reactions involved or local emissions. But knowing these connections can, in turn, direct developments and improvements within the CTM, which can then feed back into the original geophysical PM2.5 with potentially global benefits. You can also see the advantage of allowing predictor coefficients to vary in space, again shown in the left-hand panels. Here there's a very clear east-west divide in the strength of association between urban content and predicted geophysical bias, with the coefficient approximately tripling over Western North America compared to the east. Given the fine spatial scale at which percent urban impacts hybrid PM2.5, this may suggest something regionally unique in the way urban surfaces impact the AOD retrieval, or it could be a resolution impact on ADA, where the urban environment impacts this relationship on a scale below that of our simulation more strongly in the West. In either event, putting the impact of all these predictor variables together, we can demonstrate how hybrid PM2.5 offers some significant gains compared to geophysical PM2.5 alone. Here I've shown an overall global map of PM2.5 provided by the hybrid methodology, as well as the improved agreement it offers, with an R-squared increasing to 0.9 from approximately 0.7, and the root mean square difference decreasing by about a factor of 2. One of the big strengths of this approach is that it builds on the fundamental strength of the geophysical method, while simultaneously taking advantage of the constraint provided by ground-based observations. There are, of course, limitations, and first and foremost, unlike purely geophysical estimates, we now require ground-based observations, and the challenge becomes how to incorporate those measurements in a way that is most representative of your particular region of interest. Related to this, setting up a model such as GWR or alternatively machine learning-based algorithms like a convolutional neural network or gradient boosting can be quite complicated, including but not limited to the selection of appropriate predictor variables. Lastly, evaluation of these models, like any statistical models, can be quite challenging, and to that point, appropriate cross-validation is key. It's relatively easy to create a model which gives very high agreement against the data points and locations that were used to train it. It can be much more challenging to determine how well your model performs at other locations and times. With this in mind, I'm going to spend a few minutes touching on a few different methods of cross-validation. Cross-validation is a technique that's used to understand the uncertainty of statistical models. It involves the creation of a subset of data points that can be used for independent evaluation of that model. The idea being that they provide insight into how well a model will perform apart or away from the data that has been used to train it. cross-validation can be time-consuming and realistically often has to balance its complexity, accuracy, and representation. Above all, the cross-validation dataset must maintain what I would call true independence, the nature of which may depend on the questions being asked or applications making use of the resulting model. The most basic form of cross-validation is what is referred to as random k-fold cross-validation. Here we randomly withhold a set fraction, often 10% of the dataset, from model training and use the remaining 90% for training purposes. We do this multiple times until we've withheld a sufficient amount of the original dataset from at least one of the cross-validation models and use the cross-validation model's predictions of the withheld data points to evaluate the model quality. An advantage of this approach is that it's fairly simple to understand and implement. It's also perfectly suitable to many situations where the points in the dataset being modeled are themselves fully independent of one another. For our particular application, though, this last point is often not the case, with ground-based monitors often being clustered around urban centers and the concentration of PM2.5 present at one station being very much connected to the concentration that we might expect at another. Buffered cross-validation methods have been developed specifically to address this last point. The concept is that when a particular data point or station is withheld for cross-validation, not only is that point withheld from model training, but also any sites located within a given spatial distance. As with k-fold cross-validation, multiple models are trained and used to evaluate uncertainty, with the distinction being that the sites excluded from each cross-validation model are not only the cross-validation evaluation sites, but also those within the spatial buffer. The initial implementation of this approach was called buffered leave one out, or BLUE, cross-validation. It essentially withheld one site at a time plus its buffer points, running through each data point in the overall training dataset. This is effective, but as you can imagine, is also computationally very expensive, as you need to train a unique cross-validation model for each point in your dataset. Buffered leave cluster out and buffered leave isolated sites and cluster out methodologies were developed to combine the improved independence of the BLUE methodology with improved computational efficiency. Specifically, these methods withhold groups of nearly located sites plus their overlapping buffers out of each cross-validation fold, in essence running multiple BLUE-like models simultaneously, thereby providing similar information as BLUE, but with far less training of individual models. The last type of cross-validation that I wanted to highlight is temporal holdback, which is used to address a slightly different question. In this case, the focus of the model being developed is not to represent missing values at different locations, but rather at the same locations as the training dataset, just for different time periods. As before, the goal here is to separate a set of data from the training of the model that is independent in the specific way that the model is to be used. In the case of a temporally focused model, this requires the removal of specific blocks of time from the training process, which can then be used for subsequent validation. This approach does not inform about spatial uncertainties and should not be used in that way, but is quite insightful for specific temporal applications and can be combined with a spatially buffered analysis to provide a complete representation of model uncertainties. Okay, so in summary, geophysical methods to estimate PM2.5 avoid the use of ground-based monitors by using the theory-based, physically driven relationship between total column aerosol optical depth and PM2.5. CTMs are invaluable for this approach as they are able to represent all the necessary parameters and provide global coverage. Hybrid methods build on the geophysical methods using a statistical framework to predict the bias in geophysical PM2.5. And lastly, effective cross-validation of these or any models must consider how to ensure strong independence of the validation points that are being used. And now we're going to switch gears a little bit and focus specifically on the SAT PM2.5 dataset produced at Washington University in St. Louis by the Atmospheric Compositional Analysis Group, or AGAC. The SAT PM2.5 data product is the culmination of 15 to 20 years of research using aerosol optical depth to estimate near-surface PM2.5 concentrations. The goal of this long-running project is to provide a consistent, global, long-term PM2.5 dataset. In its current iteration, it is observationally constrained using both satellite AOD and ground-based observations within the hybrid geophysical framework that we've been discussing. It is monthly with regular updates provided annually and at a fairly high resolution on a 0.01 degree grid, which is about 1 kilometer. A key feature of this dataset from its inception is that it is publicly available, currently with its own dedicated website at satpm.org. On the right, you can see its basic development structure, again following the hybrid geophysical framework where AOD are converted to geophysical PM2.5 using a simulated representation of ADA, and these values are refined using a hybrid approach. At present, we do maintain a geographically weighted regression type algorithm, such as we've been discussing, but primarily we encourage users to make use of our more current algorithm that makes use of a more modern machine learning method, convolutional neural networks. I'm going to take a few minutes and address some of the unique challenges in setting up a full-fledged hybrid geophysical PM2.5 algorithm and how we've addressed these within the SAT-PM dataset. Geophysical PM2.5 all starts with AOD, so the first question we face is which AOD retrieval is best suited for PM2.5 estimation. The answer, of course, can vary in both space and time depending on the specific conditions. So to give you a better idea of how AOD retrievals can vary, I've plotted here 4 separate AOD retrievals, all monthly means of available data for April 2014, taken from the same satellite platform. 2 instruments are represented, MODIS and MISR, with the dark target, deep blue, and MAIC retrievals being applied to the MODIS instrument, and the MISR instrument having its own specific retrieval algorithm. What will strike you is how, in some ways, these retrievals are also similar, but in other ways they look quite different. Bear in mind these are all good, high-quality retrievals. Some differences are by design. Dark target, for example, was never intended to retrieve AOD over deserts, and so data over such regions is simply missing from this retrieval. Deep Blue's development initially focused on this very type of surface and well captures the features we might expect over such regions. MAIC specializes in complex terrain, using multiple overpasses to build up a representation of surface reflectance, something which MISR can do in a single overpass, but with far less spatial coverage each time, which results in an almost stuttered look for MISR, despite its high-quality retrieval, owing to its reduced sampling of the monthly means shown. In all cases, you can see data missing from the far north, where snow cover inhibits the use of any of these methods. So what can we do? We have multiple satellite instruments with multiple AOD retrievals, all of which contain useful information but not necessarily equally under all conditions. In our case, we turned to ARONET. ARONET was briefly introduced last week, and for our purposes, all we really need to know is that ARONET is a ground-based network of sun photometers that provides accurate, long-term measurements of AOD at different locations around the world. This allows the evaluation of satellite-based AOD, but only at locations that have an ARONET site. So the question becomes, how can we extend this site-specific information globally to understand the quality of a satellite retrieval anywhere in the world? What we've done is group ARONET locations together and perform separate month-specific comparisons for each satellite instrument and/or retrieval. These comparisons are grouped by land type, NDVI, or Normalized Difference Vegetation Index, and weighted by distance. We combine the findings of these comparisons based on local conditions around the world to produce a continuous, consistent definition of uncertainty for each AOD data source. You can see an example of this on the right, where I've shown the normalized root mean squared difference for dark target based on this approach. For those of you familiar with this retrieval, it shows a number of features we might expect, such as higher uncertainties over the western US, where the surface tends to be brighter, presenting a challenge to some of dark target's inherent assumptions, compared to the eastern US, where richly vegetated surfaces align very well with those same assumptions. Once we've completed these comparisons for different AOD data sources, we need a way to bring this information together so that we locally rely on each data set relative to its accuracy at any given location. To do this, we employ the relationship shown in the lower right to represent each retrieval's overall uncertainty compared to the total uncertainty of all the other AOD data sources combined. Here, a location's final AOD is determined as the weighted average of all available AOD data sources, with each one's weight based on a combination of its local normalized root mean square difference, bias as represented by the slope of the line of best fit, and its availability. This equation can be evaluated anywhere in the world, which gives us the overall weighting factors for each retrieval shown here, which provide a measure of the relative local amount of uncertainty for each AOD retrieval. What's encouraging about these results is that these spatial features make intuitive sense based on an understanding of each AOD data source. You can see, for example, dark target contributing heavily over more vegetative regions, deep blue over many of the so-called brighter surfaces, and maic contributing most over some of the more complicated conditions. We've also brought in CTM simulated AOD as an additional AOD data source, which contributes predominantly over those regions where satellite-based retrievals cannot function, such as snow-covered regions in the far north. Here, simulated AOD uncertainty follows a similar concept of comparisons against ARONET, but rather it uses categories based on speciation and elevation, which are more globally connected to CTM uncertainty than land surface types in NDVI. And bringing this all together, we can produce an overall combined AOD, such as shown here, which takes advantage of each dataset where it is most accurate. An additional challenge to bringing together multiple AOD datasets is that often there are different spatial scales or time periods. Here I've listed the satellites and retrievals as well as the model we currently use in our SAT-PM dataset. You'll note that some of the earlier retrievals available from CWIFs using Deep Blue are available from 1998 to 2010 at a resolution of 14 kilometers, whereas the most recent additions include a VIIRS instrument starting in 2018 at resolutions ranging from 1 to 6 kilometers. The Geochem chemical transport model, for its part, is run at a resolution of about 50 kilometers throughout this whole time period. One option to combine all these sources would be to simply interpolate each source down to the finest 1 kilometer resolution and combine, but this runs the risk of washing out fine-scale features when relatively coarse AOD sources are weighted against truly fine ones. To address this possibility, we combine these datasets in a tiered fashion, first averaging all datasets onto the coarsest 50-kilometer grid. We then apply the 10-kilometer relative variation in AOD within that 50-kilometer grid according to the satellite-based sources. And lastly, we apply the 1-kilometer relative variation within the 10-kilometer grid according to the maic algorithm, which is the only satellite retrieval providing information at such a fine spatial scale. Finally, we linearly interpolate the simulated AOD to PM2.5 relationship down to the 1-kilometer grid, which assumes smooth variation in eta, and apply it to the 1-kilometer AOD. As I've stressed throughout this presentation, the geophysical method relies heavily on the inclusion of a chemical transport model. The Atmospheric Compositional Analysis Group is fortunate to be a proud part of the GeoChem community. GeoChem is an advanced chemical transport model with a specific mission to advance the understanding of human and natural influences on the environment through a comprehensive, state-of-the-science, readily accessible global model of atmospheric composition. It is continually developed and maintained by an international host of scientists, many of whom are shown in this photograph taken 2 years ago during the biannual GeoChem meeting, and from the map below which shows the locations of various GeoChem contributors. For our particular purposes, representing the aerosol-driven geophysical relationship between AOD and PM2.5, it is particularly relevant that GeoChem is open source and community-driven. This allows us to include developments specific to our needs, such as recent developments in mineral dust emissions, or particular diagnostics that are well suited to ADA itself. GeoChem also boasts a detailed aerosol oxidant model, representing the inorganic sulfate, nitrate, and ammonium system, carbonaceous aerosols, and natural sources such as mineral dust and sea salts. Emissions are up to date, and include meteorologically driven sources such as mineral dust and biogenic VOCs, as well as high-resolution anthropogenic inventories such as SEDS. Lastly, biomass burning is informed using satellite observations using inventories such as GFAS and GFED. The whole system is driven using assimilated meteorology with variable resolution, but in our case, we typically run at about 50 kilometers. Hybrid PM2.5, as you're aware, depends not only on satellite retrievals and CTM simulations, but requires high-quality ground-based observations. At AGAC, we actively maintain a database covering approximately 15,000 monitor locations around the world. The coverage of this database continues to grow, as you can see from the coverage map shown here, with different colors representing ground-based monitors that were brought in during successive SAP-PM releases. This database predominantly relies on government-based networks and is limited to high-quality monitors, as opposed to low-cost sensors, which would complicate their usage in this context. Most of the data sources are publicly available, but there are exceptions, which are obtained through direct contact. I've listed the various countries and sources of the monitors we use. This includes data from OpenAQ, which is an online nonprofit specifically devoted to the aggregation and harmonization of open access air quality data, but additionally, as I mentioned, direct access to many government environmental agencies. Akin to the challenge we faced when combining multiple AOD sources over a long time period, ground-based observations are not temporally complete. That is, there are very few ground-based monitors that have been in continuous operation at the same location for the past 25 years. As a result, changes to the distribution of monitors over time has the potential to weight the adjustments inferred from these monitors towards regions with the longest histories of monitors, or worse, introduce temporal changes in these adjustments that are based on changes to the distribution of available monitors over time, rather than a meaningful representation of how the impact of bias itself has changed. To help limit this potential impact, we produce a temporally complete PM2.5 record at all ground-based monitors prior to incorporating them into the hybrid framework. To complete this task, missing ground-based values are inferred using relationships developed during overlapping periods with other available data sources. These other sources include not only geophysical and simulated PM2.5, but also other ground-based observations from nearby or related stations. Multiple techniques are used to fill in this missing data. All are compared using a temporal holdback and then combined based on their relative uncertainties. You can see the overall agreement between the inferred and observed PM2.5 on the lower scatter plot shown here, with the left-hand panel showing the agreement when other ground-based monitors are included within the inference calculations, compared to the right-hand panel, which showed the agreement when based strictly on geophysical and simulated PM2.5. A couple sample time series are shown above, with the red line showing the directly observed concentrations, the blue line showing the inferred values that have benefited from other local monitors, and the cyan color showing inferred values where no other local monitors were available. This representation of missing observation obviously adds some of its own uncertainties, but is overall very much a net benefit for ensuring long-term consistency and applying the insight gained from more recent heavily monitored time periods to earlier years. For the actual hybrid calculations, our most recent algorithms make use of a state-of-the-science convolutional neural network, or CNN. These types of machine learning algorithms are specifically designed to identify and learn from images and, in this way, are highly effective for spatial tasks, such as the relationship of geophysical PM2.5 with surrounding predictor variables. We train models separately for each month, which allows us to capture the temporal variability that we would expect from relationships between the predictors and the geophysical bias. We additionally maintain an earlier GWR-based algorithm, but this is a little bit more of a niche market. It's quite useful for a few particular applications, but in general, we recommend the CNN-based version 6. Predictor variables are in line with the GWR discussion we had previously, including satellite-based products, CTM simulations and related factors, emissions, meteorology, monitor location details, and geological type information, such as land type and elevation. We spend a lot of time developing cross-validation strategies to help us understand the impacts of and ensure an effective model away from ground-based monitor locations. These monitors provide an invaluable source of information and constraint, but they also run the risk of fooling us into misrepresenting or misunderstanding the qualities of our dataset, especially as we get farther away from these training locations. On the left here, I've shown the effect on R squared of changes to buffer radius during our buffered cross-validation analysis. In effect, this can be interpreted as how the agreement of hybrid PM2.5 changes with distance from the nearest ground-based monitor for a series of different CNN models that were created during the development of our version 6 SAT-PM dataset. The agreement of a purely geophysical PM2.5 estimate, shown in red, is independent of monitor distance, as shown in the flat straight line. Interestingly, all the hybrid models we developed performed similarly at the monitor locations themselves. If a buffer were included, however, models that excluded information from a CTM, that is, did not include a physically and chemically meaningful process-based understanding of the atmosphere, fell below the quality of a purely geophysical approach within about 50 kilometers. More advanced models that did include predictors based on CTM output fared better, but again within about 100 to 150 kilometers underperformed the results provided by the geophysical PM2.5. Our CNN model has been optimized in a way that recognizes the relative strength of the purely geophysical estimates with increasing distance to the training sites. This allows improved agreement compared to the geophysical estimates alone, even at great distance from monitor locations. Another way to look at this result is through what's called a Shapley additive explanation, or SHAP analysis. I'm not going to go through the details of this approach here, but only to say that a SHAP analysis is a method to rank the relative importance of individual predictor variables within a machine learning algorithm. I've shown such a result on the right, with the variables again ranked by their impact on the results of our hybrid CNN. As you can see, the process-based predictors and the geophysical PM2.5 itself rank as the most influential predictors, again highlighting the limitations that would be present in a more purely statistical approach that didn't build upon a physically sound framework. And lastly, the results. Here, these figures are briefly cycling through the global monthly hybrid geophysical PM2.5 dataset that we're proud to produce and pleased to make publicly available. The evaluations you see are against the highest possible standards, being both temporally and spatially buffered. The SAT PM2.5 dataset is particularly well suited for users that want to include the impact of features at a high spatial resolution and want to ensure consistency, both over a long time period, but also at distance from ground-based constraints. So in summary, AGAC's SAT PM2.5 offers a global PM2.5 dataset that uses the geophysical hybrid methodology with multiple satellite-based AOD products, an advanced chemical transfer model, and thousands of ground-based observations, all within a state-of-the-science convolutional neural network. We focus on consistency and quality, and we're proud to make this whole dataset freely and publicly available. For the last section of my part of this talk, I'd like to give a brief walkthrough of the SAT-PM website and how to access the SAT-PM datasets. For that, I'm going to switch over to a demo of the website itself. All right, so the easiest way to access the SAT-PM 2.5 dataset is via its dedicated website, which can be found at satpm.org. The main homepage, shown here, gives a brief description of this dataset with links to many of the associated information sources we've already covered today. One element I'd particularly like to draw your attention to is this form at the bottom of the page, which allows you to sign up for our mailing list. We primarily use this list to let our users know when an update has been released. Given the active nature of this dataset, this happens at least annually as we extend SAT PM 2.5's time series forward in time, which we also coincide with expanded and updated ground-based monitors and any other algorithm developments we've been working on. We really encourage our users to sign up so that they can stay informed about these updates and releases. The menus are fairly self-explanatory with access to our most recent datasets via the Data Access tab. Here you'll find our latest global CNN-based product, V6GL03, as well as the corresponding GWR-based version, V5GL06. And while not our focus today, there's also a North American regional CNN-based product, V6 and AO1, which offers a compositional dataset over North America following a similar methodology. Selecting any of these, such as V6 GLO3, will then direct you to the product-specific page. Here you'll find more detailed information related to this specific version, with a particular focus on any updates compared to the previous version. You'll also find reference to each dataset's associated publication, which will provide you a detailed understanding of the dataset's development. A little further down, you'll find details about the format and usage of the data itself, along with access to the dataset. For ease of access, we currently post this dataset at both 0.01 and 0.1 degree resolution, or about 1 in 10 kilometer, and available from 2 separate repositories. This coarser 0.1 degree resolution is much easier for file size to work with, and especially for the global files, but the 0.01 degree files are there for any projects that require it. For access, the first access point is via box folders, using the links provided. To avoid downloading the whole dataset, we've parsed the data by regions, SA for South America, AF for Africa, GL for Global, NA for North America, AS for Asia, and EU for Europe. Within these, you'll find subdirectories for either monthly and or annual mean values, and then the netcdf formatted files themselves. Access is also available via the AWS Registry of Open Data via a dedicated S3 bucket. Browsing the data via this repository is similar to the box folders, with subdirectories for region and timescale. Data can also be downloaded via the AWS command line interface with specific instructions given here. Lastly, we recognize that often the questions being asked of our dataset don't require access to the full high-resolution dataset. In fact, it can even be cumbersome to do so. To simplify such applications, we provide a select number of processed datasets via the links here at the bottom of each version's page. These links will direct you to processed national and regional summaries in a simple text-based CSV format. These files can be downloaded and viewed within any number of programs, such as Excel, which I'm bringing onto the screen here. They contain national or subnational, population and geographically weighted, mean PM2.5 concentrations by year covering the entire SAT-PM time series, as well as a breakdown of the percent of the population above certain thresholds. So if, for example, you're interested in how exposures have changed over China for the past 15 years, you could do a very quick search down to where China is being stored here, the Chinese data that is, of course. Select the last 15 years or so, as well as the corresponding PM2.5 concentrations. And then by just simply plotting that with an insert scatter plot, you can see how concentrations have changed over China or any country you're interested in for the past little while. Of course, the exact structure of doing this would depend on your exact software of choice, but it's meant to be a very simple access point for answering these very questions quite quickly. While not our main focus, we do offer a few tools and examples of accessing and reformatting the data, mainly provided by some of our users, which can help get you started on more advanced applications. The Archive and Publications tab provide access to historic versions and to our group's publications related to SAT PM2.5. And finally, the Support Team tab gives you a point of contact if you have any questions and need to reach out, as well as specific contact for the members of our group responsible for supporting and overseeing this product. Lastly, if this SAT PM product is of interest to you, I'll put in one final plug for joining our mailing list. We don't use it extensively, and so you won't be flooded with emails, but it really does allow us to most effectively inform our users when new versions are released. And with that, I'll turn it over to Pawan and Jun Hyung, who will be discussing a direct machine learning approach for surface PM2.5 estimation.
Thanks, Aaron, for covering that. Now I'm going to talk about some of the direct machine learning approach to get the PM2.5 using satellite data and model outputs. So before I start, I like to introduce three main categories of approaches used to estimate surface PM2.5 from satellite data and how direct machine learning fit into that landscape. The first two approach are geophysical and hybrid approach, which we have covered in previous section by Aaron. The third is direct ML approach. In this, there is no CTM in the loop. Instead, machine learning models learn the mapping directly from the inputs such as satellite AODs and reanalysis variable straight to surface PM2.5. Everything is learned end to end from the data. There are many examples in the community, and we'll explore one of them in here, that is Mara to CNN. Now this slide shows how a machine learning based PM2.5 product can support applications across three time horizons: the past, the present, and the future. On the left is the historical case answering question like what was PM2.5 in 2010. Here we use complete retrospective archives, long-term satellite data, reanalysis, and ground monitors. These products are ideal for exposure studies, trend analysis, and building decade-long records. In the middle is near real time. What is PM2.5 right now? This relies streaming satellite data such as geostationary, aerosol optical depth, and short-term meteorological forecast. These rapid updates supports operational monitoring, wildfire response, dust storms, and public health alerts. And on the right is forecasting. What will be PM2.5 tomorrow? These models rely only on forecast meteorology since future satellite observations aren't available and emission forecast. Forecast can help with planning, public alerts, and proactive exposure mitigation strategies. Together, these three time horizon shows how machine learning can help us understand past air quality, monitor current conditions, and anticipate future risk. The typical workflow for machine learning based PM2.5 estimation, we start with satellite aerosol optical depth and reanalysis aerosol product as the primary input. Then we bring in auxiliary variables such as humidity, boundary layer height, temperature, wind, land cover, mostly from reanalysis or forecasting models like ERA5 and MERA2. These fields helps the model understand meteorological context. Finally, we use ground-based PM2.5 observation from networks like AirNow and OpenAQ platform as target variables. All of these inputs feeds into machine learning models such as random forest, XGBoost, deep learning to produce surface PM2.5 estimates. Here I walk you through the full pipeline we use to estimate surface PM2.5 from satellite observation. We begin by acquiring data, satellite AOD and ground-based PM2.5 measurement. Next, we collocated these datasets in time and space to ensure they represent the same atmospheric conditions. Then we built statistical or machine learning models that learn the relationship between aerosol optical depth and surface PM2.5. Once trained, the model estimate PM2.5 across the satellite grid, providing continuous spatial coverage. As an optional final step, we convert those PM2.5 values into air quality index categories to support public health communication. This is a reference slide showing some example of machine learning use cases. Overall, this progression shows how machine learning is increasingly integrated into both observation-driven and model-driven PM2.5 system, improving accuracies across time scales. Here I'm highlighting the key strength and limitation of machine learning based PM2.5 estimates. Machine learning approaches are powerful because they can capture nonlinear relationship between aerosol optical depth and PM2.5, incorporate diverse predictors or inputs, and perform well even when emission inventories are sparse. They also reduce some systematic biases found in physics-based models and allow fast inference once trained. However, their performance depends heavily on the density and quality of ground monitors. They may struggle with extreme events if those conditions are underrepresented in training database. Generalization across region and time period is sometimes difficult in machine learning approaches. Okay, now let's move on to the examples of machine learning derived PM2.5 datasets called bias corrected MERA2 PM2.5 at hourly scale produced as NASA's HACAST project. Before we get to bias corrected MERA2 PM2.5, take a look at quick comparison of several major global PM2.5 products. These datasets offer in different temporal coverage, spatial resolution, and the method used to generate PM2.5. For example, DeepCam and GHAP combine the satellite, ground, and deep learning approach to provide high resolution hourly or daily estimates. Berkeley Earth relies primarily on the ground measurement with interpolation, while the Washington University datasets, which we just learned about, integrate satellite, model, and ground input at coarser temporal scale. And finally, MERA2 CNN HACAST PM2.5 product. We will learn more on it in coming slide. This slide provides some more specific details on the MERA2 CNN PM2.5 datasets, although it says only available until 2024, but periodically continue to produce the data and currently, as we will see, available until 2025. Temporal resolution is 1 hour with spatial resolution is about half a degree, which is original spatial resolution of MERA2 data product. Each daily file contains global data in netcdf format, and the recently publication provides more details on the methodology and validation efforts. Each PM2.5 estimation over each MERA2 grid comes with a QA flag. This QA flag provides a simple grid level measure of confidence in the estimated PM2.5 value. It determines by factors such as proximity to the surface monitor, land cover type, and latitude. Areas with more monitoring or a stable surface condition generally receives higher scores. The quality assurance flag range from 1 to 4, where 1 represent low quality and 4 represent highest. For most quantitative analysis, we recommend using data with flag value of 3 or 4. The map on the right shows how this quality level vary across the globe. As you will notice that the flags are higher where the ground monitor density is high. Now we will get into some details on how these PM2.5 products are derived. MERA2 provides PM2.5 component at surface such as dust, sulfate, carbon, etc. And this equation is often used to combine these components products to calculate total surface PM2.5. You'll notice that it is missing nitrate, which can be a significant contributor in certain regions. When we will validate these across the globe, we found large biases and comparison with individual station, although it shows good consistency over larger areas. Here is the map showing its global performance against ground monitors in year 2020. What we see is that bias pattern varies significantly by region and by aerosol types. In places like California, Eastern China, and part of Middle East, Marathon tend to overestimate PM2.5. In contrast, regions such as the Indo-Gangetic Plain and Southern and South America shows underestimation. These regionally varying biases highlight why machine learning correction is so important for producing PM2.5 estimates. In this slide, we summarize the key Mara2 input we use to model PM2.5 by capturing the major process that derives aerosol formation, transport, and removal. On the aerosol side, we include black carbon, organic carbon, dust, sulfate, SO2 surface mass concentration, as well as total extinction at 550 nanometer, that is our aerosol optical depth. These variables help represent both primary and secondary particle sources. On the meteorological side, we use surface pressure, humidity, temperature at multiple levels, and 10-meter wind component to capture boundary layer dynamics and atmospheric mixing. All inputs are taken at their native Mara2 spatial resolution and at hourly timing scale, ensuring consistent alignment across the dataset. Here we describe how we use reference grade PM2.5 measurement collected from OpenAQ platform as ground truth for training and validating our model. We begin by collecting measurement from more than 5,000 monitoring stations worldwide and collocating each site with nearest Mara2 grid cell. We then temporarily match the hourly PM2.5 value with the corresponding Mara2 inputs. After collocation, we apply strict quality control to remove outliers and invalid records, resulting in more than 30 million valid hourly observations. For model development, we used year 2018 and 19 data and for training, and for reserved the data from 2020 as an independent validation period to assess the performance. Here is a full workflow used to produce the bias corrected PM2.5 datasets as we described earlier. We start with spatially and temporarily collocating Mara2 meteorological and aerosol input with OpenAQ surface observation. Then we apply 5 different aerosol aware data processing strategies, each capturing PM2.5 behavior from slightly different perspective. The final product is a single bias corrected PM2.5 estimate for every single grid cell every hour with improved accuracies and regional consistency. Here is some more details on 5 different strategies. Each strategy trains its own independent convolution neural network, but they differ in how aerosol information is organized. For example, M1 is our baseline model using the full dataset with no stratification. M2 classified data by dominating aerosol species at each hour, while M3 assigned dominating species by station for the data period. M4 assign each mirror to grid cell in dominating species across the 3 years datasets, and M5 refine that by merging sulfate and carbonous aerosol as a single dominating species. Finally, the ensemble model, which is M6, combine output from all 5 approaches to produce a single more robust PM2.5 estimates. Here we show how the ensemble model M6 improve PM2.5 estimates compared to the raw MERA2 data products. On the left, you see the training data, which has data from year 2028 to 2029. The red line shows MERA2 and the blue line shows the M6 output. And on the right is the validation period, which is an independent data set coming from year 2022. So we perform this evaluation by binning observed PM2.5 into quantiles and comparing model values across full concentration range. The blue line represents ensemble, which closely track the 1 and 1 line in both the training years and the independent 2020 validation. Generally stays within the plus minus 2 sigma uncertainty band. In contrast, the red line shows that the raw MERA2 systematically overestimate low PM2.5 values and underestimate high concentration. These concentration dependent bias are clearly visible, and the results demonstrate how the ensemble approach using CNN substantially reduce these biases. Here we compare regional PM2.5 biases in raw MERA2 product with CNN corrected data. So as we have seen earlier in the top panel, MERA2 exhibit large regionally consistent error, overestimation by more than 20 microgram per cubic meter in places like California, China, Middle East, and underestimation by more than 15 microgram per cubic meter over Indo-Gangetic Plain and parts of South America. The bottom panel shows how CNN greatly reduced these biases, producing more localized and better calibrated pattern across diverse aerosol regimes. CNN correct PM2.5 also has some limitation, and it overpredict in East and Southeast Asia at high concentrations. Here is another performance metric showing the performance of CNN versus raw MERA2 PM2.5. The bar shows the medium index of agreement, which measures how well the estimations capture both the magnitude and pattern of observed PM2.5. Closer to 1 is better. Across every region, CNN performs substantially better. The improvements are especially strong in South Asia and Southeast Asia, where agreement nearly doubles compared to MERA2. Europe and United States also shows clear gains. The key takeaway is that CNN more accurately represent both spatial and temporal variability of PM2.5, providing a more reliable global data sets than the raw MERA2 PM2.5. So in summary, MERA2 CNN HICAST PM2.5 datasets provides long-term global hourly data, improve PM2.5 estimation over MERA2, bias corrected using ensemble CNN approach, and quality aware datasets. Now we'll look how to access these datasets. This slide kind of summarizes the different ways in which a user can access the PM2.5 datasets. The data landing page is the best starting point, offering an overview of the product along with key links. The README file provide detailed documentation on file structure and variable conditions. Users who prefer direct download can use the online archive or Earth data search to retrieve files for their specific time period. For cloud-based workflow, the dataset is also available on AWS. OpenDep is another option which enable remote access through tools like Python, MATLAB, or R. And Giovanni offers an easy browser-based interface for subsetting, averaging, and visualizing the datasets. Here is just a screenshot of data landing page at NASA DIS, which hosts the PM2.5 datasets from this project. Next, we'll walk through a quick demo of how to access these data in NASA Giovanni tool. So now we are going to look at an exercise using NASA's Giovanni tool to access the MERA2 CNN PM2.5 datasets and see a couple of examples how we can access and map and do the time series type of analysis online. So in order to search Giovanni page, I would just go to Google and search Giovanni. NASA Giovanni will be much better. And you will see the first link, which is NASA Giovanni. I'll just click on that. When you first time click on that link, you will notice it will ask for a username and password. So if you do not have Earth data login username and password, you might want to register and create. It's free. If you already have it, you should be able to log in. My computer already had, so it already logged in. And if you do not log in to the Earth data login, then you will have limited capabilities from the Giovanni. You won't be able to do everything. So this is homepage of Giovanni. It's a tool which actually allows visualization and analysis of many NASA's datasets. As you can see on the left side is a list of all the different platforms, variable disciplines, the datasets are available. If you actually want to explore, you can click each of these tabs like measurements, and you will see there's a lot of different types of measurements which are listed here. There's like 500 or more. You can also select by platform or instruments such as like MODIS, MERA, or whatever you want. You can also subset based on the resolution and other things. And then if you go on the top, that's where the analysis tools are available. So if you go to the select plot, it will give you the list of different type of analysis you can do. You can do maps, comparison, time series, histograms, and so on and so forth. And this is the selection of date starting and end date, and then finally you have a geographical region selection. And in the geographical region selection, there are various ways we can explore that first. So since we are going to look the MERA2 CNN PM2.5, instead of going through this whole list, I will just try to search here. I'll just say CNN, and hopefully that should pop up. So here is, as soon as I do the CNN and do the search, the parameter which I'm looking for is called bias corrected surface total PM2.5 mass concentration, all quality level, and then units and source and resolutions. And as I mentioned earlier, the data is actually now available until end of last year, 2025. So we process the data frequently. So first thing we are going to look, we selected the data. Now, first thing we are going to do a time averaged map. Okay, so I'm going to just select a map type, and then I will select a date in 2025, last year. And for some reason, I'm going to pick August, let's say pick August 8. And that is my starting, and then same date I'm going to pick August 8, 2025. So I'm just, for quick analysis, I'm just picking one day. So it has, since this is hourly data, so the total data type will be 24 timestamp, and then I will select the geographical area. Now in the geographical area, I can actually select a box, rectangular box around any geographic region, or I can actually select specific countries like, or many other US states and many other things. So for simplicity, we are going to just select a simple box over continental North America. I'm going to select something which covers both Canada and US to show a specific case here. So, and you can, if you're walking through with me, you can select any region of the world you like to select. Once you do that, so now we have selected the type of analysis we want to do, which is time average map. We have selected the date range, we have selected the region of interest, and we have selected the variable which we want to plot. Once you've done all of that, you just click on that bottom right corner, plot data. Once you do that, the system is going to go and get the data for that particular day, all 24 timestamps, and then start making plot. So here is the plot. It's very quick. You have a color scale here on the right, and then you have a map. Now, what you see here, these high values in the Canada is actually there was a huge fire during this period. So that is why I selected that specific month and day to demonstrate the capture of a smoke plume within this data set. So we can make this plot look a little bit better. So to do that, I will click on the option, and under the options, again, there is option. I will change the color scales to a little bit more to 75. And then this palette, I can actually select another palette. I'm going to select something which is a little bit more. I'm going to select this orange from yellow to oranges. And then also I'm going to apply some smoothing so that the map looks a little bit better. And then the projection is fine, and just say replot. Once I do, you can see that the color scale has changed. The values, since I only selected the maximum value up to 50, so the high values are masked. So let's go back and actually revise that and maybe go to 100 and do the replotting again. And you can use the logarithmic scale also if you like to see the plots in different. So now we can see really nice um, smoke plumes from these fires showing high concentration of PM2.5 here. So this is very simple to use tool. You can do this for any parts of the world. Now let's try another. We will use the same day, and we will just do a quick time series over this region and see how the PM2.5 is evolving throughout the day. So to do that, I'll just click again bottom right corner, which says back to the data selection. So once I do that, it goes back to my previous selection. Now I can change the plot type. I'm going to do time series area averaged. Okay. And I will keep the day same because I want to see the hourly evaluation of the PM2.5. But I will just focus on this small area where we saw very high concentration of PM2.5, just the small area, because we want to see the time step evaluation, right? So again, I changed the plot type to time series. Date I kept the same from 0 to 23 hours, and the area I have changed. Again, I'll say plot the data. And since it is averaging very small area, so it should be very fast. If you are doing this over longer a period of time, many years or larger area, then the tool can take much longer time. So now you can see a diurnal variability on August 8, 2025, and all the times are in UTC. So make sure that you remember that you can convert that into local time if you want. But you can see the concentrations are very high at the start of the day, and they started going down actually. So again, I would suggest you to actually play with this tool. It's a really nice. I can show you some other example which I have run earlier. This is another day where we have done the time series from July 1st to August, July 31st. And this is a different part of the US actually, but it does show some increasing trend. And again, this increase is actually resulting from the transport of the smoke in that part of the region. This is another one from August. You can see from earlier August, there were a lot more PM2.5 concentration than the end August. And this again influenced by the those wildfires which we have seen. So it's a really nice and easy tool. I would strongly recommend you play with different types of analysis you have here. You can do the histogram, how the PM2.5 actually looked on that particular area. So it will basically take all the data in that box which we have selected for that particular day and do a quick histogram to understand what kind of values we see. So you can see very often the values are very low most of the time, but it does shows longer tail with values ranging all the way to 100, which we saw earlier in the map also. So you can actually do a lot of good things. You can also download this as a PNG or netcdf files, and then there are other options. So I hope this tool is useful, and next week Carl will actually go through this data sets a little bit more and provide you more ways in which you can actually analyze this data along with the ground data and the satellite-based PM2.5 station. Thank you. Back to the call.
So thank you very much, Dr. Gupta and Dr. Von Donkelaar, for those overviews of the data products and their associated methodologies. To summarize what we discussed in this part, the two data sets we discussed are the Washington University in St. Louis SAT PM2.5 dataset and the NASA bias-corrected MERIT-2 PM2.5 dataset. For the SAT PM dataset, the methodology it employs is a hybrid approach where a geophysical estimate of PM2.5 from model simulations and aerosol optical depth is corrected for biases using ground-based measurements of PM2.5 on a global scale. The key strengths of this dataset are its fine spatial resolution. Gridded products are available at 0.01 degree, roughly 1 kilometer spatial resolution, as well as having a long record going back to 1998 and continuing till 2024. The dataset has consistent performance even far from the location of ground-based monitors as assessed through robust spatial cross-validation. A possible limitation to consider when using this dataset are the monthly temporal resolution of the products. So this would be unable to resolve variability at daily or hourly scales. The data are free and openly accessible via the SAT-PM website. For the bias-corrected MERIT-2 dataset, the methodology used by that dataset is an ensemble approach where a series of convolutional neural network models are developed and calibrated for different dominant aerosol conditions, and then a final ensemble model is used to select the appropriate model depending on the dominant conditions for any location. Key strengths of this dataset are its high temporal resolution. It's available at hourly temporal resolution. It also has a rather long data record from 2000 to 2024. And this dataset represents PM2.5 spatial and temporal variability much better compared to the MERIT-2 global reanalysis dataset on which it was based. A possible limitation to consider when using this dataset is its relatively coarse spatial resolution. It's available on the original MERIT-2 grid, which is a 0.5 by 0.625 degree or roughly 50 kilometer spatial resolution grid. These data are also free and openly accessible via NASA Earth data. And for example, you can use tools like Giovanni to do online analysis with this data product. In part 3, we'll be looking at a case study where we will download and compare the SAT-PM and the bias-corrected MERIT-2 datasets to ground-based PM2.5 measurements for a specific region and time period of interest. This will demonstrate both how to access these datasets and how to evaluate them in a real-world setting for practical applications. To be sure that you're ready for part 3, we're asking you to prepare in advance 3 different things. First, ensure that you have access to Google Colab. This is accessible to anyone with a Google account, such as a Gmail address, if you have that. If not, those are free to sign up for, and accessing a Gmail address or having a Google account will enable you to access Google Colab and use it during the training. Second, you'll need an account with NASA Earth Data. Again, this is a free account. You can sign up for one if you don't already have one. And for the training, you should have your username and password ready to input into the code we're using to allow you to access the NASA data. And finally, we ask you to have an OpenAQ account to access an OpenAQ API key, which we'll also be using to download data from that global data aggregation service that we discussed in part 1. If you don't have an account, again, that's free to sign up for. So you can go to the OpenAQ website and register for an account, and they will provide you with an API key. As a reminder, the homework for this training will be issued after the last part of the training, which will be part 3 next week. And in order to receive a certificate for completion of the training, you should attend all 3 parts of the training through the webinars and also complete the homework assignment by the deadline, which will be 2 weeks after the homework is issued. This is the contact information for the myself and the trainers who contributed to this part of the training, as well as for the ARSET program in general. And here are the references included in the material. So thank you all very much for your attention, and we'll move on to the question and answer portion of the training. All right, so as we transition to the Q&A, I just want to remind everyone we'll try to answer as many questions as possible in the rest of this session. We'll be recording all our answers in a document, including the questions we don't get to in the live session, and we'll be posting that document to the training website as soon as we've gone through and completed answering all the questions. So let me just check. Okay, here we go. So the first question is related, given the non-unique relationship between satellite observed AOD and PM2.5, can conditional density estimation models such as mixed density networks represent retrieval uncertainty, threshold exceedance probability, early warning, and so forth? And what validation framework is needed to demonstrate spatial transferability to monitor sparse regions? We had a couple questions similar to this, so I'll just answer sort of generally here. The techniques we've talked about in this training are 2 of the techniques, but there are other techniques such as the one you mentioned can also be applicable, and they may have their own strengths and weaknesses, which would have to be determined for a given application. But in general, the validation framework needed to demonstrate the transferability of any methodology, including the methodologies we talked about today, were the methodologies which Aaron von Donkelar covered in his portion. Those include buffered leave cluster out cross-validation to assess spatial generalizability, and temporal holdback to assess the temporal generalizability or transferability. So I'll just use that as a general opportunity to answer questions about validation. And similarly for question 2, this question is specifically about how models trained in a country can be transferred to Korea, but I'll use this as an opportunity to ask kind of the general question of generalizability and transferability of models, including the models presented here. So in this case, maybe I'll ask Aaron and then maybe Pawan to comment on this, on the more general question of transferability. So Aaron, start with you.
Sure. So, I mean, in general, I would not advise using a statistically trained model that was trained in one region to go to another. It really depends on the structure you're using. One of the strengths, when I discussed the geophysical method was it is really designed to try to be as globally applicable as possible. But really, in general, you don't want to train a model in one area to another. I mean, in either event, really, as Carl answered the first question, having a good, robust validation of any model that you want to use is really helpful in such cases. You want to make sure that if you're trying to extend the model beyond where it's been trained, you have some sort of independent data set to try to validate that.
Okay, thank you. Pawan, anything to add to that, or?
No, I think that is true. Only thing I would add is it really depends. There are many things which you can consider. One is what kind of PM2.5 concentrations and aerosols types are in different regions. So let's say you trained a model over US and you want to apply over Europe. In some cases it will work, but then as Aaron says, if you do not have any ground measurement to validate, then it is going to be somebody's guess, right? We don't know what is the quality of that. So depending on specific situation, type of aerosol, concentration range, meteorological condition, geographical terrain, and other kind of constraint, the model may or may not work. So it's really case by case determination whether it will work or not.
Okay, thank you. So moving on to question 3, what is the minimum exploitable spatial and temporal resolution for estimating PM2.5 at the scale of a Sahelian city like Ouagadougou or Kaya using MIAC or VIIRS products? So the MIAC, the MODIS MIAC and the VIIRS MIAC product specifically are available at a 1 kilometer spatial resolution. So that would be the maximum possible or the best possible spatial resolution. And these would be, these are both polar orbiting satellites, so those would be available at a 1-day temporal resolution. So if you restricted yourself to just those sources of information, that would be the best possible spatial and temporal resolution you can get. As discussed in the training, there are ways to bring in other types of information to get, for the biosecurity Merit 2 product, for example, to get the higher temporal resolution. So moving on to question 4, I think we basically answered this. This is kind of a similar to question 1, so we'll just, to sort of reiterate, yes, it may be applicable and a robust validation strategy would be needed to assess that. Question 5, are the AOD PM2.5 conversion coefficients already calibrated for West Africa or the Sahel, or is it necessary to estimate them locally? Yeah, I'll just kind of quickly, we talked about that a little bit before as well in the sort of general question about generalizability. So yes, these data sets include, the data sets we've discussed today include localized or calibrations that would make these locally relevant. But if you want to create your own data set, you would have to perform those local calibrations yourself. Anything else to add on that from Aaron or Colin?
No, not really. I mean, one of the reasons we produce these data sets is to avoid having to do your own calibrations. But there are cases certainly that aren't covered by what we do. And in those cases, yes, some local calibration can be helpful.
No, I don't have anything to add.
Okay, thank you. So question 6, how can surface PM2.5 be distinguished from elevated smoke, dust, or transported aerosol layers when they produce similar AOD values? This is a good question. We alluded to this a little bit in part 1, and then in part 2, you kind of saw the specific strategies that the 2 data sets that we talked about use. So in particular, the SAT-PM product uses the GeoChem simulation to simulate the vertical profiles of aerosols, and MERA2 uses the GoCart simulation, the aerosol simulation module. And there are also observational-based methods to look at, especially the vertical distribution of aerosol from either ground or space-based LiDAR observations, which can provide the vertical distribution of atmospheric particles. Question 7, how is the correlation between AOD and measured PM2.5 at shorter temporal scale, such as days or weeks? I'd say there's no sort of general answer to this question. It can depend on a lot of factors. For example, averaging over longer periods of time could average out some noise in the signal, but then you're also looking at changing meteorological conditions. And as we discussed in part 1, those meteorological conditions, such as humidity or planetary boundary layer height, can have a big impact on the AOD to PM2.5 relationship. So looking at a longer period of time or a shorter period of time may not help. Yeah, I'll maybe leave it there. Question 8, how can I obtain MIAC AOD data to estimate PM2.5? We put some links there for you to access those data. They're available through NASA's Earth Data site. And once we post this document to the website, you'll be able to access those links directly. But in general, if you go to the NASA Earth Data website and search for the data product, you should be able to find information on how to download it. Question 9, do the methodologies in estimating PM/aerosol apply to all other air pollutants? So that's a good question. While this specific methodology wouldn't directly apply, there are certainly ways to modify the methodology or use similar methodologies for other pollutants. Aaron, maybe just briefly comment on your group's work there.
Sure. So, I mean, as Carl mentioned, a lot of the concepts become the same. A lot of the details become slightly different. So NO2 is one our group has worked with a little bit. The idea is very similar. You have a satellite retrieval of total column NO2. You can relate that to near surface NO2 using a chemical transport model, and you can use a statistical framework to further refine those estimates. So by broad strokes, it can be very similar, but a lot of the details are often quite different and the unique challenges that come with that. So there can be a lot of work to just to copy those concepts over to a different species, but the concepts do broadly hold.
Okay, thank you. Question 10, can MLR model for PM2.5 bias correction be applied in regions with limited ground-based monitoring stations like North Africa? How do you handle missing data? Again, I think, Aaron, if you want to comment on this, but we've sort of touched on this already with some of the previous questions about generalizability, but if you have anything else to add, or Pollen, if you have anything else to add.
Not dramatically beyond what was covered in the presentation. I think this question might have come in a bit earlier on in the presentation. So hopefully we've covered some of this during our talk. But I mean, broadly, a lot of the methods that we're covering here were designed specifically to be more globally applicable, trying to handle missing data, fill in missing data, relate those relationships or figure out those relationships over broader regions as well. So they're inherently trying to account for a lot of those challenges, but again, each region is slightly unique.
Okay, thank you. Question 11, which is recommended for bright, sparsely vegetated surfaces? I interpreted this as a question about the AOD products, and in general, we tend to think the deep blue AOD algorithm is better suited for those types of surfaces. And I believe, Aaron, you did cover that in slides 28 through 34 of the presentation, where there's some examples of comparing the performance of the different algorithms in different regions. And I believe this question did come in just before you got to those slides. So hopefully by referring to those slides, this person can get an answer to their question. Question 12, okay, this is pretty specific. When evaluating intra-urban environmental exposure inequality using the version 6 global product, SAT-PM product in dense megacities, we noticed the gridded product heavily flattens spatial gradients, i.e. very low spatial coefficient of variation across districts compared to localized ground monitors that show very large microclimatic and seasonal peaks. How do you recommend researchers account for or bias correct this localized spatial smoothing when conducting fine scale, sub-district exposure, and Gini coefficient analyses? So, Aaron, I think that's a question for you.
Sure. So, I mean, there can be a number of factors affecting the scatter that you're seeing between the local monitors. I think Carl showed a slide last week that really highlighted the amount of variability within monitors within a given city, how much monitors can vary even within a 1 kilometer distance. So it's worth bearing in mind that the estimates we're providing are averaged over 1 kilometer. Beyond that, of course, it is challenging to capture these fine scale features. One of the things within we saw during my presentation, there's a lot of different resolutions of data sets that go into it. And so as much as these statistical models are attempting to account for this fine scale variability, there are a lot of resolutions going on. And so we tend to think of it as the 1 kilometer product may not fully capture those sub-kilometer features, even 1 kilometer features fully. And so we typically recommend averaging over slightly larger areas, not dramatically, up to like 10 kilometers, you can see some pretty dramatic improvement. Although in my experience with a lot of health studies, people tend to move around. And so I tend to think this is not necessarily for most applications a severe limitation, but that may depend on the particular study you have in mind.
Okay, thank you. Question 13. When we build local machine learning models or downscale or validate satellite estimates with limited ground data, our leave one station out spatial cross-validation yields a near zero spatial R squared, even if temporal validation is high. What are your recommended best practices for validating spatial models and establishing local confidence in satellite-derived PM2.5 when ground stations are so severely limited? So I would actually say that you're probably doing pretty much the best you can. So the leave one station out is probably a good cross-validation method for you, especially considering a condition of sparse ground monitoring stations. If you had more of a dense network, then probably a buffered leave one station out, or a buffered clustered leave a cluster out basically method would be probably more recommended. But in the case of not so dense ground measurements, there's probably not much statistical difference between these different cross-validation techniques. So yeah, I would say there's really no simple answer here. I think the leave one station out strategy is probably a good strategy for your case. And the fact may just be that the methodology you're looking at is not able to give you a good spatial generalization. There may just be too much variability, or you're missing information on which would explain that variability. And then my other recommendation here would be in such situations where ground monitoring is very sparse, it may actually be better to use a pre-existing product like the SAT-PM product or the bias-corrected Merit-2 product that we talked about today, and use your limited ground-based monitoring information purely for evaluation of the quality of that existing product. Oh, and sorry, I see Paul's hands up. Go ahead.
Well, no, go ahead, finish your question answer. I want to just make an announcement.
Okay, yeah. Yeah, I think that's basically what I wanted to say. So I would say the most efficient use of such sparse data would really be, instead of trying to develop your own model, use that data to evaluate the models that are already out there and see which one is the most appropriate for your setting. Okay, go ahead, Paul.
Yeah, I just want to, I think, put a note out there. I know several of you are trying to access the Mera2 CNN using Giovanni, and you are not able to find the data. And I was not aware, but I just found out that Giovanni team is moving that data sets to the cloud. So for time being, they have actually taken it off. So it will take about 10 days for them to move it. So after July 24th, the data should be available back in the Giovanni. So we apologize for this inconvenience. I think we didn't plan it ahead in time, but hopefully the data sets will be available soon back in the system, and you will be access it.
Okay, yeah. So thank you for that announcement, Pawan. We'll maybe see. I don't think that should affect your the homework that we're assigning for this. We're not using Giovanni specifically for the homework assignment, but maybe we'll just double check that that won't affect people's ability to complete the homework assignment. But yeah, thank you for that announcement. All right, so question 14. What proportions of nitrate-dominated urban PM2.5 are formed from local emissions generated in surrounding regions or transported across national boundaries, and how do these change under different meteorological and pollution conditions? So that's a very complicated question. You may be able to use something like a chemical transport model to get an answer to that question. It's really a little bit beyond the scope of today's training, so we won't go into more detail than that, but feel free to maybe contact us or first explore that training that we put a link to. And if that doesn't answer your question, you might need to contact us for further discussions. Question 15, how well does the vertical scaling of geochem capture highly localized boundary layer dynamics and low altitude micro level emission sources in extremely dense megacities? And are there future efforts to integrate local high resolution meteorology to improve this? So Aaron, I think you spoke to this a little bit in your previous answers, but if you want to add anything onto this, go ahead.
Sure. I mean, so it's a good question, and I mean, I like the idea of trying to integrate higher resolution meteorology to improve local conditions. Um, there has been some work done on like ship emissions representing subgrid variation and stuff. I'm not aware of any that specifically looks at megacities. For now, really, what we're relying on is more the statistical models to capture those any shortcomings within GeoChem to capture those really high resolution features that may come about because of those features such as megacities. It's pretty good, we think, but it's certainly an actual physically based model would be even better if we could pull it off.
Okay, thank you. Question 16, for developing countries which cannot afford ground measurements and they have a little to no ground stations and there's limited technical capacity for advanced machine learning, what would you recommend as the ideal data and method to analyze air pollution there? So I think that's, part of the motivation for this training is the fact that both the SAT-PM and the bias-corrected MERIT-2 datasets are provide global coverage and are publicly freely available everywhere in the world. The reasoning behind that is exactly to provide this kind of information to those who have more limited resources. So using these data sets that are already available to you and wherever possible, comparing them to whatever local information you do have to establish their data quality would be kind of my recommendation for the best place to start your analysis. Okay, so for question 17, given random k-fold, spatially buffered, and temporal holdout cross-validation, which of these gives the most reliable estimate of error when the model is applied to unmonitored locations and future data? So I think the recommendation of best practice here is to use both a spatially buffered cross-validation to assess the spatial generalizability, that is the applicability to unmonitored locations, and a temporal holdout strategy to assess the temporal generalizability, so the applicability to future data. Question 18, will the retrievals be biased over AeroNet locations? I'm not sure if this refers to the aerosol optical depth retrievals or the PM2.5 datasets, but I think in either case, there really shouldn't be any kind of bias specific to the AeroNet stations in either of these methodologies. Question 19, for deep investigations about the problems and possible solutions for Sahelian countries and the Sahelian alliance countries, what kind of partnership is possible for NASA ARSET with the University of Thomas Sankara University? So two points here. First, ARSET is a training program. We don't really do our own research and investigations. That's sort of something that's done separately by others at ARSET. But with that being said, the people who have participated in this training, myself and Dr. Van Donkelaar and Dr. Gupta, are involved in research around the world. So if you have specific questions or specific research topics which you think you want to collaborate on, you can reach out to us directly about that. Question 20, since process-based constraints are interpolated smoothly from the coarse 50-kilometer model, what limitations what are the limitations of using the downscaled 1 kilometer product for subgrid microenvironment or local buffer analyses in highly complex urban areas? Again, I guess this is a question for Aaron, and anything to add, beyond what you've already said, basically.
No, I mean it's a great question. It's as I mentioned before, I mean, well, actually, one thing I should say, I'm really glad to hear that you're thinking this way. Whoever asked this question, this is a great way to think about some of the limitations of the model, and it really highlights why we talk about the value of as much as possible average to a larger area. So as much as we do have statistical models and things trying to capture that fine scale resolution down to 1 kilometer, it's quite reasonable to assume that those really fine scale features will not be fully represented, and there'll be higher uncertainties. So it's a really good question. We are relying on the statistical models to capture that really fine scale and how things will vary over that really fine scale, at least how that relationship will vary over a fine scale.
Okay, thank you. Question 21. Again, this was a pretty detailed, specific question and a bit beyond the scope of this training. I think this is sort of a whole research topic in and of itself, so we can't really provide a simple answer to it, unfortunately. So question 22, to what extent does visitor traffic inside enclosed museum environments contribute to indoor PM2.5? Again, indoor PM concentrations is not really it's beyond the scope of this training, and I don't think it's really in any of our expertise, unfortunately, so we can't really comment on that in a very informed way. So let's go to question 23 next. Scroll down a little bit. There we go. Due to the lack of ground-based measurements in Africa, would you expect there to be significant uncertainties in the derived PM2.5 concentrations there from these data sets? Would you expect similar performance to be similar, better, or worse than MERA2 over Africa? So I think, yeah, maybe to Aaron and then to Pawan about regionally specific differences and uncertainties in the products.
Sure. So,
Aaron,
sorry. As the question, quite rightly implies, Africa is certainly going to be a more uncertain region. There's some challenging conditions for models to capture, both from major dust sources, major biomass burning sources, and both these methods, and Paul will speak to his, I think we are trying our best over those regions. To speak to some of the strengths of the SAT PM data set, we really have that observational constraint from the satellite very just hardwired in to what we're doing. The methods are by design using sparse ground-based measurements as much as we have available, try and calibrate that better. It's definitely a region of more uncertainties, but I would still argue that what we're producing is probably one of the better estimates that is available out there.
Okay.
Yeah,
Pawan.
I just want to add some. The Africa, as Aaron mentioned, is always very interesting region, and there's a lack of ground measurement. We all know about it, right? So it's very hard to actually assess what kind of uncertainties we might have. But I just want to let people know that there have been a lot of efforts going on in Africa in deploying low-cost sensors, although we know they are not best to use for this kind of validation, but they do provide useful information. And there are several groups in Africa and from other parts of the world who are actually trying and deploying and collecting the data. So we are hoping to actually collaborate with these groups to validate our products in future and provide more accurate assessment as we move forward in processing more data.
Okay, thank you. So question 24 was a question about actually like future funding opportunities, which is, again, not really something we're qualified to speak to, but I encourage you to take a look at the NSPIRE's website, which is a place where all NASA funding opportunities are posted for you to look at. So question 25, in my own PM2.5 machine learning framework, SHAP analysis ranked my separate satellite AOD retrieval as the weakest predictor compared to continuous meteorological and spatial features. Have you observed similar trends where the model downweights physical AOD in favor of net data proxies? So I'll just speak maybe to my own experience. I would say that this is certainly possible in specific conditions. that especially where PM2.5 might be highly meteorology dependent, there's also the possibility that there are multiple layers of aerosols in the atmosphere, and so the total AOD is really not reflective of the surface concentration very well. And also, especially if you focus your analysis on a very small region where the meteorology is similar and the PM2.5 is also similar, statistical methods might just be able to pick out on similar patterns in meteorology and AOD and make the connection between them much more easily than if you tried the same methodology on a larger region or even on a global scale, where the relationship between AOD and PM2.5 is much less consistent, and therefore other information sources like AOD would have a bigger role to play. Pawan or Aaron, if you want to add on to that.
No,
No,
I
I think you covered it. Sorry, go ahead, Paul.
no, I was just saying, going to say same thing. I think you
Yeah, no,
covered
you
it.
covered it very nicely, Carl.
Okay, thank you. Okay, question 26. How do we ensure the data is used accurately? Okay, this is a pretty broad question, but at a simple level, I'd say, this course, for one, is trying to convey to you basically what the limitations and the capabilities are of the data. So keeping those in mind as you use the data will help you to use it accurately. And as I think we've said several times, wherever possible, performing your own local assessments with locally collected data is really the best way to establish the quality of these data products for your specific region of interest. So anything to add on to that, Alan or Aaron?
I can add one thing about specifically related to the statistical modeling or machine learning method. One thing which is very, very critical whenever we do the statistical or machine learning method is the data distribution. So if you have several input parameter and you're trying to map with the output PM2.5, do check how the data is distributed, because machine learning algorithm and statistical methods often try to learn what is around the mean, and the extreme values become actually has less impact on the relationship which is formed. And often you will notice that these methods either underestimate the very high values because there are very few data points in your training, and overestimate the low values because that's again very small values in your overall data set. So the data distribution checking and adjusting your validation data versus the training data can be an important aspect of uh, preparing your data before you start modeling, whether you use a multiple linear regression or linear regression or machine learning method. It applies to all of those.
Yeah. All right. Thanks. That's a really good point about the extreme values, especially if you have a special interest in the extreme values as opposed to the mean, then that's an important caveat to keep in mind. Okay, yeah, let's maybe move on to the next question. Scroll down a little bit to question 27. Will the ML-based estimate capture events such as dust storms and smoke from fires? So, Pawan, do you want to speak to this a little bit?
Sorry, I was muted. I think it will capture the MERA2, as written here in the response, does assimilate satellite-based aerosol optical depth and the fire emissions. And if that event is captured by the satellite specifically from the MODIS, then the MERA2 should have it captured, and the machine learning based bias correction should actually capture it. In some cases, it might, if the machine learning training didn't have dust or smoke type of cases, then it might miss. So there are certain cases where smoke is very thick or dust plume is very thick, and the satellite sometimes get confused whether it is dust or cloud and mask it as a cloud, and it does not get propagated into the assimilation stream, and that can actually be not seen in the MERA2. So I would say it varies case by case, but in general, it should be able to capture uh, qualitatively. Quantitatively, things can be very different, and depending on which event and how far we are looking from the location of the source, the quantitative numbers can be different, but qualitatively, it should be captured.
Okay, thank you. Question 28. What are the main challenges in making PM2.5 products like the Washington University SAT PM 2.5 or the Meritu CNN HeyCast product from retrospective processing to near real-time delivery? So this is a question about like the data latency and how maybe how that might be reduced in the future. So I guess yeah, Aaron, go ahead.
Sure. So as I wrote, I mean, that's a great question. We'd love to be able to get data sets out even faster. It's unfortunately it's often not practical. There's, as I've written here, as you've gathered from the presentation, there's an awful lot of different data sets that come together to make these final PM2.5 data sets possible. From biomass burning emission inventories, which need to be brought into the chemical stress models. Models need to be run. One very practical example of a delay that we face is to get the highest quality ground-based monitors. Often governmental agencies will perform their own internal checks for usually about 6 months. So really for next year's release, which we're planning to put out later this year, we're just starting to work with the ground-based monitors now, which are the highest reference grade monitors. That as well as our own internal validations take time. It's really multifaceted why it takes us so long, but really feel that the time gives us an opportunity to produce the highest quality data product that we can.
Okay, thank you. Pawan, if you have anything
No,
to
I
say
think
about the, yeah.
it applies to the Mera 2 or any other satellite product in the same ways because they all depends on some ancillary data sets. Specifically in case of Mera 2, it assimilates so many data sets. So to get all those data, prepare that for assimilation, it takes some time, and Mera 2 is reanalysis is always, I think, several weeks behind because it's a reanalysis. The idea is to retrospective analysis. So I think that is why we want to produce the best available data sets. And there are some real-time and forecasting mode data products which have a different way of processing.
Okay, thank you. So question 29, this refers to a specific slide where we're talking about the index of agreement and asking about some of the other metrics. So some of the other slides did have different metrics, especially bias, and then also the paper describing the data set itself, which we'll link here, obviously has a much more detailed description of the performance. Okay, question 30. Is the SAT-PM dataset available for North Africa? Yes, it is. And what is the spatial and temporal resolution? It's 0.01 degree spatial and monthly temporal resolution. We covered that in the presentations. Question 31. Okay, another regional question. In Indonesia, the days with the worst air pollution, for example, haze from fires, are often the same days covered by clouds. So these days get removed from the data, the AOD data specifically. How do we fix PM2.5 estimates so they don't end up too low because of this? Aaron, maybe I think you answered this question here. So
Sure. I mean, I'll speak to how we address that within the SAP PM data set, and maybe Pawan has more to add after. Within SAP PM, we account for these, sampling bias in a few different ways. First off, the ground-based monitors themselves, first off, the SAT AOD, we correct it to a monthly mean based upon sampling adjustment factors provided by the CTM. So again, using that chemical stress model to infer how the days we've observed relate to the days we haven't observed, and then providing a more representative overall monthly mean. Subsequent to that, the ground-based monitors themselves will sample irrespective of that cloud cover. So when we apply those machine learning models or GWR models as a subsequent calibration to the geophysical estimates, that inherently also corrects for any sampling biases that may be from limitations to the satellite retrievals themselves. So there's a few ways in which this is hopefully addressed. None of them are obviously perfect, but there should not be inherently a sampling bias due to cloud coverage days in our product.
okay,
Yeah,
Uh,
I,
yeah, go
for
ahead.
Mera 2, I think as it is a model produced data, so the data should be available even if there is our cloud. Now, in terms of the bias, I think the bias can arise because if the satellite AODs are missing, then this model is relying completely on its own capability. Uh, I don't think we do any specific correction to actually account for that sampling bias there. But we haven't seen any clear evidence in our validation studies that it should have a biases.
Okay, thank you. So question 32 rather is a follow-on, I think, asking about which of these image satellites would work best for Indonesia where there are cloud covered. So just in terms of this is maybe a little bit more general, but a geostationary satellite like Himawari offering more frequent observations would give you more opportunities for cloud-free observations. However, any of these instruments would be, I think, similarly affected by the presence of clouds. And I also just want to note we've gone a little bit over our allotted time. If it's all right with Aaron and Pawan, we might keep going for maybe 10 more minutes and answer some more questions. And then anything we don't get to live, we can answer in this document offline. Yeah, so let's keep going for a little bit longer. Question 34, you mentioned that multilinear regression is used to predict geophysical bias in PM2.5. Could you specify which independent variables or predictors are typically used in the SAT PM MLR model? So I think to save time, we'll just sort of refer you to the publication where these are listed, and then in general, they fall into the categories of geophysical and process-based parameters, emissions, meteorology, and site location. I believe Aaron covered this in the slides as well. So question 35, within the workflow of the M6 ensemble predictive model developed for the MERA2 CNN HKS dataset, what is the scientific rationale for training 5 distinct convolutional neural network strategies rather than relying on a single baseline strategy, basically the M1 model? So, Holland, if you want
Yeah,
to speak to that briefly.
sure, sure. So I think as we have discussed and seen in many cases, that the relationship between input parameter and the output target variable PM2.5 is not linear, and it varies as a function of aerosol's type, metrology, range of PM2.5, and many other parameters. And our goal was to what best we can do, right? So in order to actually get the best of the data sets, we uh, divided the data into different dominating aerosol component type so that we can get a better sense of how the input to output mapping can be done with more reliability. And that is why we actually try to play with different schemes, and then we came up with these 5 different model which provide us an optimized solution. It may not be the best, but it provide an optimal solution which work globally, and then the ensemble kind of bring them together in a more unified consistent data sets across the globe. So to use the strength of Mera2 and their aerosol component, we use those different approach to get an optimized global PM2.5 dataset.
All right, thank you. Question 36, quick clarification. Slide 63 notes that the ML generalization across region and time isn't guaranteed, while slide 78 calls MERA2 product robust to unseen regions and years. Given that it's trained on 2018 to 2019 and validated on 2020, could you help me understand what robust to unseen regions and years is based on? Paulin, if you want to answer
Yeah,
the question.
so I think we continue to evaluate this data, although in those years which we have mentioned in the Those are based on the published work which we did, but we continue to evaluate, and I think we haven't seen any degradation in the model performance over even beyond 2021 and 2024, which we have done recently, which is not part of this paper. So I think it what we can say is robust over time. Now, over the region, the problem is the same as we have been discussing in earlier question, is that if there are not ground stations available over certain regions, then it's very, very hard for us to actually even predict what kind of uncertainties or error might be there. And that is why we try to provide a quality assurance flag with the data sets, which basically rely on the ground density of the ground measurements and few other parameters which are important in our training algorithm, and that gives you an idea about whether a product is reliable in certain region or not. So I think the quality assurance is one way to kind of see whether the product is robust or not.
Okay, thank you. Question 37. How do geophysical models handle sudden extreme local emissions like crop burning or wildfires, especially when satellite AOD observations are missing due to cloud cover? Aaron, if you want to add anything on that.
Sure. I mean, this probably ties a little bit back into the earlier question, why it takes so long to put these, estimates
Mm,
together each time. So within the geophysical model, it's obviously driven by a chemical transport model. And so in our case, and we use daily biomass burning emissions. And so those would capture within those daily inventories, day specific events like a sudden residual burning or wildfires. And those emission inventories themselves aren't necessarily dependent on the same don't have the same limitations, don't have the same limitations as some of the AOD retrievals. So a number of those daily biomass burning inventories can work just fine even when there is some cloud cover. Now, that's not to say they're perfect, of course. I know crop residue burning has received a little bit more attention in a few papers I've read recently, saying that that can be a higher uncertainty. But for the geophysical estimates, they're trying to do it within those daily inventories. And one of the reasons we, of course, enhance the geophysical estimates using the hybrid approach is to try to account for any misunderstandings or underrepresentations that occur within those inventories. So that's kind of how we account for it.
mhm. Okay, thank you. And question 38, another question about Indonesia. Due to the persistent cloud cover, which for the machine learning methods, which meteorological variables or predictors are the most crucial to include so the model doesn't become biased in a humid tropical region that experiences extreme humidity fluctuations during hotspot seasons? I guess, Paul, if you want to, offer suggestions there, or this might just be something that would need to be studied. But yeah, go ahead. Go ahead.
Yeah, let me just read the how Indonesia tropical persistent cloud cover throughout the year for most models. Yeah, this is a real problem, I guess, and it is not only over Indonesia. This is if you look across the ITCZ, which is has a consistent cloud cover, even over South America, over Africa, part of that, and satellite, the current passive satellite observation of aerosols will always have that problem, because if there are cloud, the signal is so dominated by the cloud, we cannot really get any information about aerosols. So I don't think there is any observational solution there. We will have to rely on the model for that. And more we can improve on the model, I think the better answer we can get. The other option is rely on ground measurement and active satellite-based observation, which are few of them right now in orbit, and the few more coming in the future, which should be able to provide some more details or aerosol information in presence of cloud. And once they get assimilated into models, we will have better idea what is happening in those regions.
Okay, thank you. And then I also saw another question just came in, which was also referring to Indonesia. I think you have probably answered this in your response as well, about the general challenges. So I think we'll read through these and make sure that we've captured all of them. But I think for the sake of time, we're gonna I think call an end to the Q&A here. So thank you very much, Dr. Van Donkelar and Dr. Gupta, for contributing your time and your expertise to this training. And thank you very much to our attendees for your interest and all these very interesting and insightful questions about how to use these data sets appropriately. As a reminder, the next and final part of the training will be next week. And to prepare yourself for that training, you should test out that you're able to access Google Colab, the have an Earth Data login password for accessing the NASA Earth Data, and also have an account with OpenAQ to access the OpenAQ data set via their API. And there'll be some links to those. The slides will have links to those when they're posted to the training website. So yeah, again, thank you everyone, and we will see you next week.